Like a steam turbine, the gas turbine's main function is to turn a generator to produce electricity. Your duties as an operator are likely to require you to operate both steam and gas turbines. All turbines work pretty much the same way. They extract energy from a fluid as it moves from an area of higher pressure to an area of lower pressure. The main difference between gas and steam turbines is the fluid that makes the blades spin. In a steam turbine, the fluid is steam. In a gas turbine, hot combustion gas turns the turbine. Combustion gas is produced by burning a fuel, such as natural gas or fuel oil, in combustors. The temperature of the hot gas generally ranges between 1,800 and 2,300 degrees Fahrenheit as it enters the turbine. Combustion gas passes into the turbine through a set of stationary blades called nozzle guide vanes. The nozzle guide vanes, or just nozzles, direct the gas into the rotor blades at a fixed angle. Gas turbines generally have either 1, 2, or 3 sets of blades. Each set of rotor and stator blades is called a stage, just like in the compressor. On some turbines, the tips of the blades are linked together by a band known as a shroud. The shroud reduces vibration and adds strength so the blades can be made out of thinner metal. This illustration will show the components of a typical turbine. Each set of blades is attached to a separate disc made of special alloy steel. The discs are bolted to each other and to the turbine shaft. This type of turbine is known as an axial flow turbine because the gases flow through it parallel to the turbine axis. Let's follow the combustion gas flow from the nozzles in this view of the turbine blades. These are the stationary nozzle guide vanes, and these are the rotor blades. The hot gases rushing out of the nozzles hit the rotor blades and push them aside, making the turbine spin. The gases then move through the stator blades, which direct the flow into the next row of rotor blades. There are 2 basic rotor blade shapes, which we'll show in cross-section: the cup-shaped impulse blade and the reaction blade, which is similar in section to an airplane wing. This is a single turbine rotor blade, and these are cross-sections of its shape at these points. Most turbine rotor blades today are completely impulse-shaped at the base and gradually change into a pure reaction shape at the tip. The reason for this change in blade shape is that the tip of the blade moves faster than the base because the tip has to cover a greater distance during each rotation. The streamlined reaction shape moves more smoothly at high speeds through the flowing gas than does the cup-like impulse shape. This illustration of a single turbine blade attached to the disc shows why the speed at the tip is greater than the speed at the base. This distance is much longer than this distance. So this part of the blade must move faster during each rotation to cover the greater distance than this part, which doesn't travel as far. Hot gas flowing through the blades provides the energy to turn the turbine, but it can also cause a lot of damage. The rapid temperature changes turbines go through when moving from cold start to operating speed can cause blade material to become brittle and crack under stress. High temperatures also are responsible for turbine blade creep. Creep is a gradual and permanent growth in the length and width of the blades caused by repeated heating and cooling. The reason for creep is that blades subjected to hot combustion gases expand each time they're heated and contract when they cool. The amount of contraction never quite equals the expansion. The blades never return to their original size and grow a tiny bit larger with each heating and cooling cycle. Blade growth is never more than a few thousandths of an inch, but it may exceed the close tolerances required in the turbine chamber and cause the blades to rub against the casing. New super alloys and protective ceramic coatings have improved the turbine blade's ability to withstand high temperatures. Some experimental turbine blades are completely ceramic, making them even more heat resistant. Compressor bleed air also can be used to cool down the turbine blades internally and protect them from heat. Many modern gas turbines have hollow shafts and discs. Cool compressor air is forced through the hollow shaft to cool the disc directly by convection. This also helps cool the blades. Heat moves from the blade into the hollow disc, where cool air carries the heat away. Other turbines carry this a step further. The blades themselves have small holes along the edges. The holes are connected by channels to airways in the disc and shaft. This allows cooling air to pass through the blades. You've now seen the details of gas flow through the turbine, rotor and stator blade interaction, and blade construction. You've also heard about some of the problems caused by the rapid temperature changes turbines go through and ways to protect turbine blades from excessive heat.